All right, and that is now loading up. Let's go ahead and begin. All right, let me see what I got. Okay, so the last time that we were here, we were spending a lot of time talking about insight. Now we are going to move on to probably one of the best known computational models of problem solving. We're going to talk about Herb Simon and Newell's general problem solver. Okay. So this is Newell and Simon's general problem solver. I am occasionally going to call it a GPS. Please do not get that confused with GPS that helps you navigate your car. So this was a computer program that was originally developed for well-defined problems. So as we kind of talked about a couple of days ago, well-defined problems are situations where you have information about your initial state, you have information about your goal state, and then you have information about the different strategies that will get you there. So one thing that I will mention, of course, is that very few problems that we encounter in our everyday life are well-defined problems. So this is really only a simulation for a very, very limited set of problems. In addition, Newell and Simon basically equipped this computer program with serial processing, a limited short-term memory, and the ability to engage in long-term memory retrieval. And so in particular, what they were interested in is what Newell and Simon referred to as a problem space. And they did this by utilizing what is referred to as a think aloud protocol. So for those who may not know, we don't really spend a lot of time in cognitive psychology really having people internalize and be introspective about their thoughts. So we talked a lot about the problem of introspection in early psychology and why that was a problem. Back in chapter 1, we talked about the fact that it can be incredibly subjective and things like that. But we do have what are referred to as think aloud protocols, and those are ways that you can actually get an idea of somebody's internal mental state without referring to the subjectivity or dealing with the subjectivity of introspection. So the idea behind a think aloud protocol is you basically train your participants to think, verbalize all of their thoughts out loud, any thoughts at the moment that they're having them. And you get really, really well trained on this. So you have to report them in a certain way. You're trained to report them in a certain way. And here's what's most important. When people use think aloud protocols like Newell and Simon did, they're not necessarily looking for underlying mental states. They are looking for potential qualitative sources of evidence for certain types of strategies. And they can also acknowledge, they also do acknowledge that these strategies can differ from person to person. So the problem space is something that you're able to get a handle on with the Think Aloud protocol. If you'd like to learn more about Think Aloud protocols, Simon, along with Erickson, actually wrote a book called Protocol Analysis. I had to take a graduate class on it. I actually took it as an undergrad to get a really good letter of recommendation. But if you're interested in learning more about protocol analysis and think aloud protocols, I have a book in my office. You are more than welcome to borrow it. But this problem space basically consists of 3 different things, much like what we would see with a well-defined problem. We have the initial stage of the problem, we have our goal state, and we have potential strategies, which are referred to as mental operators. I'm gonna sip some tea. Right. Anybody need some more time? Okay. So here is an example of the general problem solver in action. So how do we solve problems using the general problem solver? Well, Newell and Simon basically said that there were a few different strategies that seemed to be incredibly helpful. The first is what's known as a heuristic. And if you've had me for general psychology, you've heard me talk about a heuristic. A heuristic is a very simple thinking strategy or a rule of thumb that you can use to help you solve a problem. So we're going to talk about two of those problem-solving heuristics today. We're going to talk about one referred to as means end analysis and another that's referred to as hill climbing. And then the other possibility is an algorithm. With an algorithm, all possible outcomes are computed. So it's almost like an anagram solver, basically looking and working through all possible letter re-scrambling combinations to give you the actual answer. So for example, if we use a heuristic, we can actually solve the Tower of Hanoi problem pretty quickly. With something like a means end analysis or hill climbing, the goal will always be to kind of keep our end goal in mind. We want to make sure that all of these disks are moved from this peg, and we want the exact same configuration on this peg. But there are a couple of different strategies that we need to be able to do this. First of all, we can only move one disk at a time. Second of all, we can never put a larger disk on top of a smaller disk. So a heuristic might be a pretty simple strategy to help us figure it out. An algorithm is eventually going to get you the right answer, but it's going to look through all possible configurations of moves. And that means that that's going to take a lot more time. So what we tend to find with problem-solving heuristics is that heuristics tend to be quicker, but they're also more prone to error. In contrast, algorithms are eventually going to get you the right answer. They're accurate, but they're also very, very time-consuming. So I'm going to start by talking about the strategy of hill climbing. So hill climbing is basically the strategy. Do you need me to go back? Okay. Okay. So hill climbing is basically the strategy that you are always going to make a move that gets you closer and closer to the goal. So hill climbing is basically every step should get closer and closer to the goal, like climbing to the top of a hill. But one of the things with hill climbing is that there are definitely some limits to it. So this is actually a really cute kind of example. So we have a dog and there's an open fence and a bone with a bowl in it. Now, according to hill climbing, the dog should always choose a step that gets it closer to the goal. But because of the way that the fence is currently positioned, what the dog will actually have to do at some point is take a position right here that actually moves it further away from the bone, very, very briefly. So hill climbing can be a little bit of a problem because, for example, going back to our Tower of Hanoi, sometimes, so hill climbing would basically say every single move you make should get you putting a peg on one of these two discs, or a disc on one of these two pegs, because it should always get you closer to the goal. Bless you. But hill climbing never really allows for backward tracking, and sometimes to correctly solve a problem, sometimes you have to put a disc back on the first peg and work backwards before you can move forwards. So it's more of a simple strategy. It also tends to be used more often when you don't really have a good understanding of the problem. So always getting closer to the goal seems like a good solution. But if you're always picking something that gets you closer to the goal, you're not going to be able to appreciate the instances in which you actually have to move farther away occasionally to actually get to that goal. So as the picture kind of notes, this strategy will fail since the dog first needs to move away from the bone in order to reach the bone. And generally, you're going to be looking for the step that leads to the greatest improvement toward the goal is also another thing to include. Okay, everybody good? Okay. So means end analysis is a little bit different. Means end analysis acknowledges that sometimes you're going to have to move farther away to get where you want to be. So in this case, you have to actually notice the differences between your current state and your goal. And then what you're going to do is you're going to form a sub-goal that reduces those differences. And then you keep doing this until you reach the goal. So you meet the sub-goal, and then once you've met that sub-goal, you then reevaluate. You pick another sub-goal, you meet that sub-goal, you reevaluate, you create another sub-goal, you meet the sub-goal, and you just keep doing this until you reach the goal. So for example, your textbook kind of gives you this example. Suppose your wash basin is leaking. They're British. So your sink is leaking. Your problem-solving strategy, after having held your finger against the leak a few times, most probably will be to find somebody who can fix it or someone who may know someone who can fix it. And those are examples of means end analysis. Another example is, let's say that I'm going on an airplane to Florida. I'm not actually doing that. I am probably not flying for a little while. But let's say that I missed my flight and I still need to get to Florida, but to get to Florida, I'm going to have to take a layover that's actually going to put me in New York rather than Florida. And traveling to New York is actually going to take about as much time as going to Florida will. But to end up getting to Florida, I first have to go to New York to get a connecting flight to Florida. This is an instance where I'm actually moving further away from my goal, but I've created a sub-goal that will help me reach that goal. Okay, everybody good? All right. So is a GPS model actually a good model for what we do? As I kind of mentioned, it's really good for well-defined problems, but as I brought up, most of the problems that we encounter in everyday life are ill-defined. Additionally, this model typically does not take into account how often we solve problems on the basis of insight. Additionally, a couple of other things that are important to kind of note, especially based on means end analysis and hill climbing as potential strategies, it's going to specify the shortest possible sequence to take, or the shortest possible sequence to the goal. So for example, I have a Tower of Hanoi puzzle in my office. According to the variation of the puzzle that I have, to actually solve the puzzle, you have to make 127 correct moves. But I can tell you, when I mess with that puzzle and when other people in my office play with that puzzle, they do not get 127 correct moves. They make mistakes. They have to backtrack. They have to start over. And the GPS model is not going to do that. It is going to assume perfect accuracy, perfect strategy use, and no mistakes in specifying this shortest sequence. But that's not how most of us actually really solve problems. Most of us do not always take the shortest sequence. Additionally, because the GPS is equipped with a short-term memory and a capacity for long-term memory retrieval, it's really good at remembering prior steps to solving a problem, what was previously done to solve the problem. But there's not really much talk about its planning ability. And solving a problem not only requires you to remember the previous steps that you took, but it also requires you to plan ahead. So this may not be, it's good for a certain type of problem within a very, very limited range, but as a model for how humans solve problems, particularly those ill-defined problems, it's not very good. Okay, so now we're going to talk about transfer. Does our ability to solve certain types of problems actually carry over at all? So I want to talk just a little bit because it kind of relates. I want to talk a little bit about brain training programs. So about 7 or 8 years ago, how many of you started noticing like a rise in brain training programs, especially for the elderly? So I think Nintendo had games like Brain Age for the DS. We have a copy of Big Brain Academy for the Nintendo Wii. And of course, you could not get away from ads about Lumosity. And so right around the time that I had gotten my PhD and was starting my postdoctoral work, there started to be a lot of talk about whether brain training programs or different types of programs could actually enhance your abilities or your working memory capacity. And this was supposed to be the really hot new thing, because if you can train people to modify their working memory capacity, remember that working memory capacity is involved in almost every single thing we do, cognitively speaking. So if you could modify that, that would be a huge deal, and it would help things like reading comprehension and logic and reasoning. So here's the problem, and here's what we ended up finding, and here's why we don't really talk about brain training that much anymore. So if I go onto Lumosity, or if I used Lumosity 7 years ago, there are going to be a variety of tasks that I can do. And the more that I do them, the better that I get. So I get better at these tasks. But that's not really what I'm interested in. I'm wanting to see if what I've learned in this Lumosity program actually carries over to other types of tasks that are not necessarily related. So I want to see if improving my working memory, for example, can make me better at logic and reasoning. Can my knowledge carry over? And what we found with brain training programs like Lumosity is that they make you good at the tasks themselves. You get what we call near transfer. But what you don't get is far transfer, and far transfer is more important. So this is where I tell you, unfortunately, and I have to be a little bit of a buzzkill here, the brain training programs do not actually work. And I do believe that Lumosity got into a lot of trouble making claims that it could not deliver on. So we're going to talk about the issue of transfer. So transfer is when we can use our previous experience from solving a previous problem to help us solve a similar problem. And this is what's known as positive transfer. So there have been instances where I've gotten a flat and I've had to change a tire. And I first learned how to change a flat with one particular type of car. Then I get a different flat with a different car. I can use my knowledge from the previous instance. Now, obviously, there are going to be some different things. The spare might be in a different place. My jack might be in a different place. But I can use my knowledge and my previous experience changing a flat to help me change this new flat. This would be a case of positive transfer. Now, on the other hand, sometimes our previous experience actually can hurt our ability to solve a problem. And this is what is known as negative transfer. Give me just a minute, my glasses are fogging up. Okay, everybody good? Ava, do you need a little more time? Okay, all right. So let's talk about the importance of transfer. So I've taught you a lot of things in this class, such as different types of ways to enhance your learning and memory. And hopefully, some of what I've said can be used outside of the classroom as well. So ideally, the information that you learn in this class and other classes should really facilitate additional learning and utilizing what you've learned in class outside of the classroom, even for topics that are not similar. And this is what's known as far transfer. And this is kind of the problem that brain training programs often have. They train you very specifically for similar tasks, but they don't necessarily carry over into different tasks. And so often the problem with brain training programs is that they don't have that far transfer. Now, on the other hand, if I teach you to do a certain task and you do well on a very similar type of task with a similar context, this is what would be known as near transfer. So when we talk about the effect of transfer on problem solving, we're often going to be talking about near transfer because far transfer is significantly harder to get. Everybody good? All right. So we're going to talk about 3 different dimensions of transfer. So when we're talking about whether or not something will transfer, we need to consider 3 different aspects. So first of all, we have a task similarity. And this can include things like superficial features. So for example, maybe you're asked to solve 2 problems that have to do with a king and an army, but the underlying structure of the problems is ultimately different. So superficial features include things that are not really relevant to solving the problem, such as the overall framing of the problem. And then we have the structural features of the problem. So this is basically the causal relationships between the main components in the problem. And we'll talk about superficial and structural features in a little bit. We also have context similarity. So noticing similarities in terms of location and social context. And then the time interval, the period of time between when you get one problem and you get another problem. So with context similarity, that could be, are you solving both of these problems in school? Are you encountering these problems in 2 completely different environments? Are you in the same cultural context? And then the time interval is basically the time between when you get those 2 problems. And we tend to find that transfer is often greatest when the problem or the task similarity and the context similarity are very highly similar and the time interval is short. I was typing on the chat and I didn't realize it was doing that. I shouldn't have done that. I was going to tell the people on Zoom a knock knock joke. That didn't work. Hey, Brianna, do you still need to get some stuff here? I'm sorry, I didn't mean to do that. I was like, how did it do that? I don't know how it did that. Okay. So here's a study of bar transfer. So this comes from Chen, Mo, and Hono Mitchell in 2004. So I'm going to read you a story. You don't need to write this down. In a village by a river, a chief guards a sacred stone statue. Every year, the chief goes downriver to the next village to collect taxes. There, he places the statue in a tub at one end of the hanging balance. To pay taxes, villagers fill the tub on the other end of the scale with gold until the statue is balanced. This year, the chief forgot to bring his balance scale. How can he figure out how much gold to collect to match the statue's weight? So take a minute or 2 and see if you can solve the problem. If you have an idea and you're in the chat, go ahead and type that in. So take maybe about a minute to think about the solution to the problem. And let me know if you find a solution to the problem. Hello, did anybody get the problem? I'm going to give you 1 minute to figure it out. All right. Does anybody have an answer? Anybody in class have an idea? No? Okay. So you're going to get it once I tell you. So what you have to do, you got to take the tub, put it in the river, put the statue in the tub, mark the area, mark the water level on the outside of the tub of how much water has been displaced, and then take that tub back and fill it with gold until it reaches that line where it would be displacing the same amount. So you basically put the gold in the tub until it hits that mark once it's in the water. So you basically use water displacement to help you solve it. Did anybody get that? You did? Why didn't you tell me? Well, it was right. Don't be afraid. Dr. Gilchrist isn't going to judge you if you get the wrong answer. I'm just going to say that was really a creative idea, but it's not the correct answer. But yeah, water displacement is how you solve this problem. So here's what's really interesting. For people in China, there is actually a very famous folk tale that involves just such a solution, which means that it has very, very high task similarity. In contrast, I know of very few folk tales here in the United States that involve such a solution. So when Chen and colleagues gave this problem to both people in China and the United States, 69% of people in China were able to solve the problem because they have a story that exists that can be mapped onto the current problem, but Americans do not. And as a result, only about 8% of Americans actually solved the problem. And so based on this, Chen basically said that there are 3 different stages of bar transfer. So what you have to be able to do is recognize that there is a similar story somewhere. So we have what's referred to as accessing. In this example, accessing is basically being able to remember and being able to access a previous task that has that similarity in terms of the problem structure. So you have to be able to access that previous exposure. You then have to be able to map that previous story onto the current problem. And then you finally have to execute the problem solving with that mapping in mind. So these are the 3 stages of bar transfer. We're going to do a few more word problems today. So if you're zooming in, I know that it's hard to focus when I'm showing you slides and talking, but if you have any ideas or thoughts on how to solve the problem, please feel free to share. Okay. All right. Are you ready for some new problems? We're not there yet. So when we study FAR transfer, it turns out that context similarity really plays a role. Researchers had participants either solve problems either in a laboratory or in a classroom location. And much like we kind of saw with encoding specificity, it's kind of clear that there is a memory component here. We do find that when our location stays the same while we're solving problems, you're going to end up getting more FAR transfer. And that probably has to do with the fact that, again, the environment around us and our context can actually serve as a really powerful retrieval cue. The other thing that really seems to matter is the role of time interval. So researchers have looked at how well hypothesis testing strategies in children. So for those of you that have had me for research methods, we're not talking about null hypothesis testing or anything like that. We're talking about informal hypothesis testing strategies. And these tend to transfer better. These problem-solving strategies will transfer better, again, when the time interval is shorter. Okay, so here's the problem. You don't have to write this down. So a doctor wanted to operate on a tumor. He wanted to use a laser, not use laser, but use a laser to eliminate all of the affected cells, and he had to make sure he got them all. However, the laser beam could also damage the adjacent cells. The tumor was large and had to be taken out all in one operation, though the continuous use of the laser was bound to affect healthy tissues as well. What could the doctor do? Does anybody have any idea how to solve this? Raise your hand if you think you have an idea. Raise your hand if you have no idea. Raise your hand if you would like a hint. Okay, here's a hint. If you weren't able to solve this, let's add a hint, which is another problem. A general wanted to capture a castle. The castle was equipped with cannons and could easily target any advances and blow up armies with ease. The more concentrated the army, the worse the problem. The general knew that the best way to capture the castle was to accumulate all his resources and attack it in a single operation, though he was afraid that any concentration of this force would be faced with lethal cannons. Sorry about the spelling errors. He didn't want to risk his soldiers so soon in the invasion and allow them to get demotivated before even reaching the castle walls. Did that help? Raise your hand if it did. Raise your hand if it didn't. Raise your hand if you noticed some similarities between the two problems. Very good. How would you like one more hint? And then you'll be able to solve the problem. One day, it suddenly occurred to him what he needed to do. He decided that instead of sending his entire army in one operation and risk fatalities, he could divide his army into battalions and send them as smaller waves, one after another. Now, the cannons couldn't reach all of them as the invasion force was not as concentrated as before, but they could still all accumulate on the castle walls and put pressure on the enemy. Indeed, he carried out his plan and captured the castle in record time with minimum casualties. Now, do you have a better idea of how to solve the problem? So instead of using the laser at full strength, you have smaller waves and you slowly surround the tumor that way, so you're not damaging the healthy tissue by blasting it at full strength with the laser. Can you see the underlying similarities between the two problems and the ultimate solutions? So this is what is called problem solving by analogy. So here's what's kind of interesting. So this was originally a study by Gick and Holyoake in 1980. And you can kind of see how well we actually do with transferring analogies. So we have our control condition. And you can kind of see here, this is a weird graph, but this is based out of 100%. Almost over 80% of people never got the answer. A few people are able to get it without a hint. Most people don't get it though. So here's what we find with the general story. Maybe about 40% get it without the hint. Once they get the general story. So once we get that general story, in addition to the X-ray story or the laser story, people can get it without the hint. Some people get it with the additional hint that I gave you of how the general solved the problem, but very few people never get the problem. So you can kind of see here that even giving somebody a problem that looks very similar and has a similar underlying structure can be enough to help people figure out the problem. So research on transfer has typically focused on this analogical problem solving. You're trying to look for the underlying similarities between the current problem and other problems. Now, how do we successfully solve these? Here, what is absolutely critical is that you have to notice the similarities between the current and the previous problems. It's why I asked you, did you notice that those problems are similar to each other in their structure? If you can't notice that, you're not going to be able to understand the similarities and solve the problem. So I'm going to go ahead and stop on this slide. So once you are done writing, you are free to go. I will see you here on Friday. We are going to finish up talking about problem solving. We're going to talk a little bit about expertise, and then we're going to talk about judgment. Not like judgy judgment, but judging the likelihood of things or judging coin flips and things like that. So hopefully you'll have a lot of fun with that, and I will see you here next time. So go ahead and finish writing this down, and then once you are done, you are free to go. right, thank you very much. All right, and I will see you all later.